welcome to CMPE59G. Today's lecture will be given by Cansu Canbek. Cansu is a postdoc in our research group. She is a PhD in chemistry. So today she will be talking about the experiments we're doing in our research group and also provide you the background information required for such experiments. Okay, thank you.
Thank you for the introduction. And again, welcome. We already have a small discussion before the lecture, but to start with, as Professor Tugcu stated, I'm a chemist. During my studies, I work really in different fields, but this one, nanonetworking, is the most different and the most interdisciplinary one for sure. And you're going to see why. Because what we are doing in nanonetworking, we're combining chemistry, we're combining biology, and we're combining computer engineering, as well as electrical and electronical engineering. So it's quite a challenging field and new field that you're going to, you already are familiar with. And now I'm a postdoctoral researcher here, yes, but before I was working in France in Atomic Energy Research Center. My main field is the nano production, nano engineering, experimental point of view, not theoretically, as you are. And today I want to speak about how we are building a nano machine by just starting with the building blocks, what we call nanoparticles. I'm going to introduce you what are these nanoparticles, what are these building blocks, and how we are producing them, how we are characterizing them, and finally, how we are producing a nano machine that is able to work inside a human body or elsewhere in another environment that you want them to make, make a complex task, you give them. And again, when you are working with nanomachines, what you want is to actually make them collaborate with each other, first communicate and then collaborate with each other. And this collaboration can be achieved again by using nanochemistry. So when you say nano, it's actually mostly chemistry. I'm sorry for this, for the computer engineers. But if you have any question, please don't hesitate, because I can use some chemical terms. I know you're not familiar with it. Just stop me and ask me, okay? It's important. First, as I say, during this lecture, what we are going to see is the basic concept in nanotechnology. You're already familiar with this term. And you know that what we are doing in nanotechnology, we are trying to make the things incredibly small, but not just making them incredibly small, but the idea is make them smart. Okay? In nanoscale, we want a material which is smart and which can do quite complex tasks that you gave them. All right? And just a second, I will see point of here. So, when you're doing a nanomachine, first, you have to imagine how we can build a nanomachine. What can be used to construct such a machine, all right? For this, one is actually the most common used material is the nanoparticles. These nanoparticles can be different materials. It can be metallic nanoparticles, it can be polymeric nanoparticles, biological molecules. You can combine them. So I'm going to explain what are these nanoparticles in the next session. But they're quite important because nanoparticles are everywhere. And I'm sure you don't know this, but you know that there's a titanium nanoparticles inside the cakes you want. You just eat, you know, the birthday cakes. In this birthday cakes, the surface is quite smooth, and you see that they're quite shiny, bright. This is because titanium. I'm sorry, you're eating them. So you have to know what's nanoparticle, right? And when we build a nanomachine by using a nanoparticle or biological molecule, the idea is to make them work with each other, right? In the nanonetworking cases. So how can we increase the capacity and the capability, let's say, the single nanomachine by just trying to make them communicate with each other, right? This is the goals of today's lecture. And here you can see the outline of the lecture. There are a lot of headlines, just don't focus on them because ideally I want to explain everything connected with each other, what we do, why we do it, and of course when you produce the nanomaterial, how you characterize them. So it's going to be like a smooth passage, I hope, for you, right? So let's start with I don't want to go into detail what's a nanomachine because you already know this. And I'm sure you already seen this definition like 1,000 times before this lecture. So nanomachine is a single device that it's capable to work at incredibly small scale, 10 to the minus 9 meters. And at this scale, you can give them different tasks. You can make them to store an information. You can make them deliver an information, or you can use them as carriers, like drug carriers, or like when you want to load something into a nanomachine and deliver from one point to another, and then release this information or release another, I don't know, molecule. You can make it by just using an external stimuli, and your nanomachine is going to work as a delivery agent. It's like a courier, like a carrier. So it's quite smart materials. And in this scale, it's really hard to build such a machine, because when you think about it, it's like a science fiction, but it's real. And that's why I like it, I think. And these nanomachines are actually, when you want to use them inside the human body, of course, there are some barriers that you have to pass, which is important because you have an immune system, and your immune system does not accept everything. Like you cannot inject anything in the human body and expect them to go anywhere. That's not possible. What's important is that when you want to, depending on the environment you want to use your nanomachines, you have to build them in such manner. So what I mean is that when you're going to use an inorganic nanoparticles, let's say, inside the human body, you have to understand that your immune system is going to attack. So you're going to have a biological barrier. But you have to pass this. So how we do it? How we do it? We combine nanoparticles with biological molecules to build a nanomachine. In this case, you actually cheat your immune system. So it's going to be a little bit like going from the behind door, but your immune system is going to be free of any attack. So you can make them to work wherever you want. And of course, when you're going, depending on which side of the human body or the living cell you want to use, these biological barriers, or the membranes, let's say, have a defined sizes. So your nanomachine should be in accordance with the sizes of the pores, let's say, or the membranes. So it should be compatible with where you want to work with. So that's why it's a little bit like a designing first and then building. Okay? As I say, when you are going to build a nanomachine, before making them to communicate with each other, first you have to build them. When you want to build a nanomachine or nanorobots, like it's quite the same thing, when you want to work with them, of course, you have to couple different type of molecules and you have to combine a complex system in nanoscale, meaning that it's like a nanoengineering, like nanostructured engineering, and it's quite hard in experimental point of view. Theoretically, it's easy. You can just think it's a chemistry, mix it, and then we have something. No, it's not like this in the real case. And why it's going to be hard, I will show you in the next parts. And of course, when you use a nanoparticle, you have to understand that nanoparticles are smart materials, but single nanoparticle works for nothing. So again, these nanoparticles should be smart, should be communicating with each other, should be forming a structure, and then you can build a nanomachine. That's the important point. First, you have to work with a nanoparticle to build a nanomachine, right? And of course, when these nanomachines are interacting with each other, you can make them to do more complex tasks, more challenging tasks, or like a task that is not like it's really like a science fiction you can think, but yeah, they are doing it. And here, let me show you the 3D structure of a nanoparticle. It's not the size, of course. And this is a decahedron. It's actually 3D structure of gold and silver nanoparticles that you can use. It's just a single cluster, all right? What we have here, we have a lot of different atoms, you see. Atoms combine with each other to form really specific structure. It's like you have 5 different crystals orienting along a single axis, like we have a single X here, common X. It's a 1-1-1 axis, we call it. And we have 5 different crystals orienting around. And here, As you can see, there is a smooth surface. It's a 100 surface, what we call. It's a crystallography. But this particle is actually smarter, when you think about gold, than a bulk gold, like a gold bar. You can say no, because I'm sure that you want a gold bar instead of a nanoparticle if I ask you, and I would say the same thing. But the thing is, this is more expensive. It's really weird, but this is going to be more expensive. Because when you go from a bulk gold to actually a nanoscale gold, you're going to see that you are going to gain a lot of properties. Like, these properties can help you a lot of way. And I can tell you that because we wanted to buy this such of material before we produce it in 2015. And 1 milliliter solution of gold nanoparticle was 350 euros in 2015. 1 milliliter solution. So it's really more expensive than a gold bar. But you cannot sell it in a black market, so it doesn't work for you. And when you start with, for example, a bulk gold, and you go to the nanometric scale, okay? You have a single nanoparticle. What changes? You decrease the scale, of course, your material becomes smaller. You organize the gold atoms, or silver, or metallic atoms, or anything, any material. In a nanometric scale, you do a nano-engineering. You construct atom by atom. It's a really different way to do a construction. But you make atom to communicate with each other and organize in such manner, all right? It becomes cleaner because it's less toxic, not for human applications, but for storage. It's less toxic, and you can use it in many different fields. Other than bulk gold, you can only sell it. So, of course, okay, when you sell it, you can buy an application also, but still. It's cheaper to produce, yes, but not cheaper in the final product. And if you consider another nanoparticle, let's say other than gold or metallic nanoparticles like a silica or zirconium or, I don't know, titania, which actually exist also in the toothpastes that you use, they are not so expensive, so it's like an easy production. But for metallic nanoparticles, especially for expensive nanoparticles, it becomes cheaper to produce them, all right? They become faster. I'm going to show you why they become faster, because you are going to gain a lot of properties. And what is it? It's in the next slide. But when we say faster, it's faster for catalytic purposes, because your material is really quite active. Not like a bulk gold, which is inert material, because gold is an inert metal. But if you go to the nanometric scale, this property is going to be stopped. So you have an active material that you can use for any application. And more important, it's more functional. What's functionality? The functionality is actually gained when you have an active surface. If you say a metal is or a material is active, it means that you have a lot of active surfaces that you can use, available surfaces. I can attach a biomolecule. I can combine this, I don't know, with different type of materials for a reaction, enzymatic reaction, catalytic reaction, anything else. So in nanoscale, you have a lot of active surfaces. And you can see that here. For example, you have a bulk gold, really large size gold, all right? You have a lot of, as you see, like gold atoms on the surface, and you decrease the surface, you decrease the scale. So you start with metric scale and you go to the nanometric scale, all right? Here, of course, you have a lot of surface atoms, but you also have a lot of bulk gold, actually the gold atoms, inside the spherical shell. And when you look at the particle diameter, if you decrease it, the number of surface atoms is increased in the nanometric cases. You have a lot of surface atoms in a nanoparticle than a bulk material. What happens if you have a lot of surfaces? As I said, this surface is active. You can use, because since it's active, in nanometric scale, you increase the reactivity of your material. And then you gain some catalytic purposes, which is not our point here. I'm not going to discuss the catalytic reactions with you, don't worry about it. So, this is one of the properties that you gain when you decrease the size. It's quite important because now we have an active material. We can use it inside the human body or elsewhere, that you can functionalize, you can play with it, you can attach with anything you want. So it's like gaining a little bit more smarter than the bulk material. Another one is going to be a little bit more complex to explain. But let's start like this. Do not look at this side, for example. Let's just focus on the left side. Imagine you have a spherical nanoparticle, all right? It's never spherical, just to explain you. When we say spherical, of course, it's still crystal structure. You see that it can look spherical, but of course, we still have some facets. This is an icosahedron. You have like a lot of active surfaces, 1, surfaces. You see like there's a triangle, okay? So you can use this particle, as I said, for the coupling or for functionalization. Another thing is, this metallic, especially for metallic nanoparticles, when you irradiate your solution, your sample with light, there are some surface electrons in this material because it's a metal, okay? It's not isolated, so it's like a metal, you have surface electrons. And under light irradiation, this surface electrons starts to oscillate. Okay? They start to make this oscillation move, and you see this oscillation is collectively, so the charges actually oscillate with this light irradiation. And this oscillation yields a quite nice peak in a spectrum, and the range of this peak or in the spectrum can be changed. For example, here we are in the UV region. Okay? This is the region where your eyes can see. Okay? And I have a solution. I irradiate it with light, and I see that there's a color change, and I see that there's a peak, a signal, meaning that I stimulated my solution and I have a back response. Normally you don't have this with the bulk material. Now you have a signal back. It's like information. You just irradiate it with light and you see that there's a response back. I can use this signal for many different things, for diagnostic, for biomedical applications, I don't know, for treatment of cancer, and how I'm going to show you next. And this research is actually being conducted in a lot of hospitals, and it's like in the clinical trials, and they're using gold nanoparticles inside the human body to treat the cancer. That's why they're expensive. And this property is quite important for us because it's a unique response for different material. For each different metal, you have a unique response. Okay? For spherical nanoparticles, completely symmetrical nanoparticles, we have only one single response. But when I change to 2D structure, meaning that a nanorod, it can be, I don't know, it can be bipyramidal structures, nanowires, like long, or carbon nanotubes, for example. In case of carbon, it's more complicated, but you can imagine the structure. It's like a, it's like a cage structure. You have a carbon nanotube, which is quite hard material. In these 2D structures, you have two different oscillations. You have a longitudinal oscillation. The surface electrons can oscillate in the longitudinal manner, and it can oscillate in the transverse manner. So this is a peak resulting from the transverse oscillation, and this is the peak actually resulting from the longitudinal oscillation. And the thing is, this peak is quite sensitive to the aspect ratio of your nanoparticle. Meaning that when you change length divided by the diameter, meaning the aspect ratio of your nanoparticle, you can play with this peak, and you can have a system which gives you a response in the near infrared region. You can go up to the 1,300 nanometer, 2,000, 3,000, 4,000. You can increase this, or you can come back to the redshift, and you can see that you can have a response somewhere here. So you can design a material where you want a response. Okay, it's another property that we use actually when we are working with the nanomachines. Okay. Here are some of the examples that you can see for the nanoparticles. I know that it's one of them is quite interesting for you, and I'm guessing it's going to be the Invisibility Cloak, because everybody is familiar with the Harry Potter, and I know that when you're a child, everybody wanted something like this. And actually, this is a research. Really, Invisibility Cloak is a research is going on with the metal nanoparticles to have a completely reflective surface like this. And there is a bigger scale of this, and in aerospace engineering, as you know, for the airplanes, to be disguised, like hide from any detection, they're using metal nanoparticles as blockers. which creates a completely reflective surface, actually scattered surface, let's say. And in this case, you do not have a detection of a completely large size airplane when it's flying. So it's aerospace engineering is really using a lot of metal nanoparticles for such kind of research. And all these applications are actually, let's say, outside the human body. I just wanted to show you what you can do with the metal nanoparticles. And one of the oldest one that has been used, actually detected the use of nanoparticles, is in the church windows. You see, this is, I don't know if you have ever been in Notre Dame Cathedral in Paris, and you cannot do it right now because it's burned. And if you ever have a chance, just check the windows and you're going to see that there are a lot of colors. And this colors is not actually stemming from the dye or anything, no. They have used gold and silver nanoparticles in this age, actually, when historically that there is no way to produce nanoparticles, but they were capable, and nobody knows how. It's quite interesting. And of course, as I say, because of the surface plasmon resonance property, each particle, when you change the shape or the size, here there are different sizes. It starts a little bit small, like 50 nanometer to, let's say, 100 nanometer. I cannot see it clearly. And because of the size effect, you see that there are different scattering light, so you have a different color. And you can use it for nice purposes like this. It's one of the oldest one. There are different things that you can create completely hydrophilic or completely lyophilic surfaces, which means that it does not, for example, the smart window, this Pilkington's smart self-cleaning window, is currently in production, and you can apply it in your windows in your homes, but it's expensive. And mainly these big companies are using it because they have nanoparticles dispersed in a resin, and they cover the glass with it. And every time it rains, it collects all the dust and the grease from the window, so you don't have to do anything. So this is one application of the nanoparticles for the smart application. Another is for the clothes. I know that Nike actually is producing this nice clothes that is not getting any sweat or dirt, and that's how they do it. They're using nano coatings. Another one, as I mentioned before, for the biomedical applications, before this measurement devices, the electronical ones, there were disposable devices. Meaning that when you have a small blood, when you want to measure your glucose level, you have a small blood, you just put it on the disposable device, and through the diffusion, you can see where is your glucose level, because there's a little bit, again, hardcore chemistry behind it, because glucose and glucose oxidase react with each other, and there is the hydrogen peroxide which is coming out, which degrades your material. So let's say you start with the 50 nanometer particle, and because of this reaction, you have a peroxide which shrinks your nanoparticle. And when it shrinks, meaning that the color is going to change, because you're going to change in the surface plasmon resonance. So you're going to detect directly where is your glucose level. This was one of the applications, and still there are some uses in the glucose sensing, and they are using it for the electronical devices also, electronical measurement devices. But of course, there are some other methods that you can use. Last one I want to talk about is the infrared absorbers, because it's quite important that they are using nanomachines also for the infrared absorbers. They couple it with not biological molecules, but two different nanoparticles, and they're active. And the activation is actually coming from here. For example, imagine you are in a closed environment such as this. You have a single window, all right? What is the main heat source? It's the sun. But the sun, of course, there are different lights, like different, let's say, type of lights inside. You have a UV light, you have an infrared light. And of course, when you have, for example, in a hot day, the main source of the heat is the infrared light inside the sun's emission, all right? So what they are doing, they have some metamaterials produced from nanoparticles. They just dispose it like a spray disposal on a window, And this material can transmit the light, so you don't have any, you don't need any external stimuli or external light, but it blocks the infrared, meaning that you don't have to use any air conditioner or any cooling reagents. So it's like a gaining cost, like actually reducing the cost, so gaining a lot of economical points for the big companies. This research is being conducted for really a lot of different companies because using a heat or cooling agent inside such an environment is really costly. So everything is about cost reaction in here. Metamaterials or the nanoparticles help us to do this, all right? And if you have any questions, please let me know.
I think they use this technology in Burj Khalifa in Dubai when they're building it because there is lots of sun and it was turning like an oven.
Yeah.
So like preventing that use this technology.
Exactly.
Cold particles in there.
Also, they're doing it for the automotive industry because there's like a black body inside your car, you see, and you're using mostly air conditioning inside the cars, not just the houses. And automotive industry is really working a lot on such an application. So you have to prevent the black body, so you have to do a lot of, so for them it's really economically good, let's say. For the research point, of course, these are, as I say, the external applications. But for us, what we are doing in nanonetworking, mostly we are interested in the clinical uses, right? For the biomedical and for the health applications. Because, you know, the health industry is growing a lot and we still have a lot of problems that we did not solve. And for the clinical use, as I said before, when you want to use a nanoparticle or nanomachine, let's say, let's stop the nanoparticle here and go to the nanomachines. When you're going to use a nanomachine, you have to pass our defense mechanism. You have to make sure that your nanomachine is able to go everywhere you want in the human body, or the point that you want specifically, right? That's important. And for that, to pass the biological barriers and our immune system, you have to combine an inorganic material with the biological molecules. What are these inorganic materials? You can have, as I said, the inorganic nanoparticles, metal nanoparticles, they are actually. The one that I showed you before, like a gold, silver, titanium, like you can imagine palladium, these are different nanoparticles. You have some polymeric nanoparticles, you have some organic nanoparticles. For such system, you don't need any biological barrier passage, so it's like an organic molecule, it's like not needed. But these particles does not have the same property as inorganic nanoparticles. So they are, of course, they can be used, but they're more limited, right? You have some nanocrystals, or you have a carbon nanotube, as I said initially. But if you're going to use inorganic materials, as I say, you have to couple them with a biological molecule. What can be? It can be DNA, okay? When you want to produce a nanomachine, which can be used for a cancer detection or cancer elimination, you have to build it specifically for a patient. So each nanomachine does not work for every human being. So it's like a person-specified medicine, let's say. So what we are doing is we are developing something for each patient, all right? And let's say you want your machine to do more complex tasks. I want my machine to first detect the cancer and then use this machine as a carrier to load a drug and release the drug in this point, all right? In the point where I want them to go. In this case, it's possible that you can combine different nanomaterials and you build a machine by just combining these materials and to create a synergistic effect. This definition of synergistic effect is quite important because, as I said, this active surfaces lets you to combine anything you wanted easily. The chemistry allows us to do this. I can attach here a biomolecule, I can attach another nanoparticle, I can attach a second nanomachine coupled with a second nanomachine, let's say build a more complex system. That's just because of the active surfaces that is gained in nanoscale, all right? So, and what's happening currently in the nanomachines for the anti-cancer devices? How does it work? Let's say you have a nanomachine, you use the biological molecules to pass the barriers where you want them to go. But these biological molecules can also be used for biorecognition. meaning that it's like a key and lock relation. Your biological molecule is going to recognize where does it want to go in the human body, and it's going to lock the point that you want, okay? And then it's going to release the drug, your nanomachine. This is the system, what we see here. And they are using here like a DNA aptamer. As I said, DNA is the most commonly used biological molecule for biorecognition, because it has your stamp, directly your code inside, and you can use it to deliver information easily, right? And what happens, for example, for nanomachine when I want to use them to eliminate the cancer? How do I do it? First, the biological molecule inside your machine reacts, okay, recognize the cancer cell, because there's specific for DNA. It recognizes the cell, it binds with it by this biorecognition, it connects with it, and then, as you remember, when I say about the surface plasmon resonance, you have an emission of light, and then you have external stimuli, you have a response. Remember the SPR response. It means that your nanoparticle is actually absorbing an energy. And by just doing an external illumination, external stimuli, you can make your nanoparticle, your nanomachine actually, to release this heat which is absorbed, and it burns and it kills the cancer cell around by just absorbing the light. That's quite interesting, because SPR is the thing is for the nanoparticles mechanism to kill the cancer cell as a photothermal therapy agent is working like this, basically. Of course, it's more complex than what I explained. And the thing is, it just burns the cells around, so it's a really small surface. And when you're using, for example, chemotherapy or some other things, the thing, you cannot control where you burn or when you harm the cell. You can also kill the living cell. But for nanoparticles, this region is quite small, so you can control where you want to kill, or when you want to do apoptosis, let's say the cell death, all right? That's why nanomachines are really smart to work with for the biomedical purposes. Do you have any questions up to now? All right, let's continue. And of course, as I said, there are a lot of applications, there are a lot of things that you can use with the nanoparticles or the nanomachines in different fields. But how we do it? What are we doing when we are producing this? Before production, you have to design it, as I say. The design stage is quite crucial, because you have to know what you want in the final product, where you want them to work, and how they're going to work. This is quite important for us. So, let's say we choose an application. I want to use them in a human body, or I want to use it for, smart window. I have an application, all right? And we work mainly with the theoreticians in this case, with the computational scientists. They are doing first the simulations that we wanted, meaning that, for example, for each application, we choose a material. Okay, we say this material can work for such an application. They take this material and they create a simulated response. Okay, this is the response I want, for example, in infrared region. I want when I stimulated my particle, I'm not going to stimulate you, but when I stimulated my nanoparticle, I'm going to have a simulated response same as this, all right? And then we design a synthesis method. We just choose a method to produce it, and then we check experimental results. So if the experimental nanoparticle is correct when it's characterized, and the result, the experimental response, does not match with the simulated response, we have to first do a parameter control. Okay, we check what we have done wrong. It's possible that you can change, you are not working with the right conditions. It can be not right pH, it can be not right temperature, and different things can work. So we just do a parameter check, all right? And when you do a parameter control, you work with it, but you still don't have the same response you wanted. Then you come back, again, the theoretical case, and you say this material is not producing this kind of things. There's a lot of experimental parameters, so that's why we always have to work with the theoreticians. We never do a blind synthesis. That's important. The blind production is actually like working really in a completely dark environment, you have something but you don't know why. So that's why every time when you are going to do for an application, like final application, you have to work with the theoreticians. Like you have to first design a simulated, let's say, response or simulated idea. Like you have to know what application you want, and then you have to do the synthesis, all right, for the production. We are doing like a small scale synthesis, but this can be like a big scale synthesis for an industry, and in this case, you're going to lose a lot of money. Let's say I have the correct response, okay? I have a simulated response. How can I produce a nanomaterial? First, what you can do, you can start from bulk material. By just shrinking it, you can produce nanoparticles. And when I mean the shrinking it, there are different methods. It's not just crushing, and there's also crushing. There's a method called explosion. And I'm sure most of you will love it because it's really like a industrial scale, and you just explode the material. It's quite interesting, I think, but we don't do this. And you produce nanoparticles. And some of the people call this barbaric production. My old professor used to call it. And what you can do in another way, you can start with atoms, and you can construct first clusters, a little bit like a bigger scale materials, like a binded atoms, a little bit smaller than a nanoparticle, and then you produce a nanoparticle. So it's like a bottom-up production. This is more common. Let's say this is more interesting to do it for us. Because here you can control, and it's like more precise production. Here you are not able to precisely choose the size of your nanoparticle, okay? These are some of the production techniques, as I mentioned, and the explosion is, as I say, it's one of the techniques that is being used. But most common used method is actually the wet chemical synthesis from the bottom up and the sol gel process, because this two process does not require like a complex equipment. It's just in the laboratory. You can just do it by, I want to say simple chemistry, but it's like mixing it, basically. But for the other one, when you want to use aerosol process, or when you want to do a bioreduction or vapor deposition, you really need complex machines, complex structures, and you need the equipment for this, right? Mostly what we are using is wet chemical synthesis in our laboratory. And let's say you have the material, okay, you produce it, you know how to produce it, you have everything, and how you characterize it. Okay, you cannot say, I just produced this, take it and use it. No, you have to characterize your material correctly. If I produce the right size, if I produce the right composition, if I produce the right properties, if the electrical properties of this material is really what I wanted. That is the important point. There are different techniques, and I'm not going to go into detail of all of them, because in nanonetworking, basically what we are using is microscopy and spectroscopy, right? And I'm just going to explain you three different ones, which is important for us, is optical microscopy, because in nanonetworking, our test beds are based on the optical microscopy, right? And you have electron microscopy, force microscopy, it's like atomic force microscopy, scanning force microscopy, STM is scanning tunneling microscopy. There are different fields. It's basically the same thing. The idea is to have an image of your nanoparticle. It can be a 3D image, it can be a topography of a surface, it can be anything you wanted. And this technique is just based on what kind of, how do you say, final image you want and what you're using to have this final image. For optical microscopy, as you see, we are just using incident light. For electron microscopy, for imaging, instead of light, we are using electrons to capture the image. For force microscopy, we are just doing a, how do you say, we're just checking the reaction force between the tip of the machine, and I'm going to show you, and the surface to create a 3D topography of an image of a surface, all right? Spectroscopy is another technique which is used mostly in characterization of nanosystems, and mainly UV visible spectroscopy that I showed you before. In the surface plasmon resonance, you have a peak, as you see, and we characterize this peak by using a UV visible spectroscopy. I'm not going to explain this section really. If you have any question, you can ask me, but it's quite analytical chemistry. So just let me know if you want to know more. All right. This is an optical microscope that currently we are using in also our research here. As I say, mainly you capture the light. See here, you have a camera on the top and you have an incident light coming from the bottom. We use a visible light, okay, to create an images. And the thing is, you just magnify actually you increase the magnification by just changing the lenses. You have an optical lenses inside the column here on the top, okay? And this, by using the light as a source and coupling it with the CCD camera, it's a charge coupled camera, you just can create an images like this. But this images is actually in nanometric, so it's micron scale, but the particles are nanometric here. These are the best images you can have it with incident light. It's not possible to gain an information about the composition or about really the structure of material with the optical microscopy. It's not the right tool. You can just detect your particle, you can see them, but you cannot do anything more, okay? This does not give you the correct information. If you want the correct information about the composition or the structure of your particle, you have to go more complex structure. This is an electron microscope. It's a transmission electron microscope.
But going back to the optical system, it's an easy and cheap and small size solution that could be used, for example, for implementing sensors.
Exactly. Exactly. It's depending on the final application, the final result, what you want. If you want the composition, as I said, you cannot use it. But let's say you just want to have an average idea like about the size of your nanoparticles. You can use it. That's no problem. But just make sure that you choose the right tool to characterize the right material. That's the important things for us. I will show you some videos that we have for the nanonetworking in the next cases, and they're captured with this microscope. They're quite interesting, and we love it actually. I love it.
You're starting a new project in the 1st of April based on this.
Yes. Yes, we have another project, so I can also introduce you this. So going back to the transmission electron microscopy, as I say, in this microscope, the main source of record is actually electrons. You use electrons to capture an image, not light. Here you have an electron column, then you have a couple devices here, and then you have a cooling system in the behind, so you need a room like this to have a transmission electron microscope. It's like really large equipment, and it's really sophisticated equipment. And as I say here, the column represents, in this case, you have an electron gun on the top, okay, which gives an electron emission, okay? And then you have some, of course, again, optic lenses, like you use some mirrors, let's say, not the lenses, sorry, the mirrors, and you try to focus your beam directly on your sample. And what you do, you again have some here CCD cameras and some other detection devices, and you just count the electrons which is transmitted from your sample. So the image is created with the transmitted electrons. There's another one, it's called a scanning electron microscope, which uses the scan to create topography. Here we check the scattered electrons, okay? Depending on which type of backscattered electrons or transmitted electrons, depending on what you detect, you create a different type of images. And you create different type of analytical methods, okay? Here are some of the images that we have for, from transmission electron microscopy. These are my images. I try to make them to show you because I wanted to use them to explain you how we take it and what are they. Here are gold nanoparticles, gold nanorods, the ones that I gave an example in the beginning. They're, as you see, they're quite homogeneous, but we have some spherical nanoparticles, maybe you can see, or some short nanorods. But still, this is quite monodispersed solution. The size here is about average size, let's say, 30 nanometer by length and 10 nanometer by diameter. Here is again gold. We have a star structures and bipyramidal structures. You see they're quite pointy, these nanoparticles. And we use these nanoparticles for catalytical surfaces because you have a lot of active surface since it's quite pointy and you have a lot of a lot of surface that you can play with it. Again, here we have a gold-silver composition, two types of nanoparticles, and what we call them bipyramidal structure, because it's like a pyramid but double pyramid. Okay, each particle, each different shapes can have different applications. Here we have some silica beads, if I was not wrong. Yeah, silica nanoparticles. They're a bit larger than what we have. As you see, scale is 1 micron. And silica nanoparticles can be used also for the smart windows, as I explained you, or for different kind of applications. Here we have a core shell nanoparticle. Core shell, what I mean by core shell, as you see inside we have something a little bit more dense, and we have some more bright dots on the top, right? Or this is a inverted image, and this is actually the regular bright field image. So we just do the image processing from one to another. On the surface, you have a gold, like a gold antennas, because I love playing with gold and working with gold. And you have gold antennas on the surface, and you have a silica nanoparticles inside. Why we do this? It's quite interesting, because silica nanoparticles are dielectric, okay? They do not give any response as a plasmonic response what we wanted. And since cost is important for industrial applications, and I want something like a structure like this, instead of doing a completely big size gold nanoparticles, we just fill inside with silica and use the gold outside. And we couple the properties of silica and gold together. This is a core shell system that is quite, you can use it for a low cost production. And by just melting the silica inside, you can have such kind of structure. This is a gold bubble or gold halo structure, you can say it. You have a gold outside, and inside there is nothing. Actually, this particle is obtained from this particle. We just melted, it's like explosion of the bubble. It's like you just put a needle, the silica is gone, and then you have a gold halo structure. And we call it gold cages. And there's a lot of applications for this material. Another thing is, for example, what you can obtain is halo silica structures. This is a halo particle. It's a mesoporous particle. Meaning that I just play with I just melt the gold outside, and I have the silica nanoparticles, which is mesoporous. See, there's like cavities on that in them, and I can use this to attach my biomolecule for the cancer detection, because you have an active and you have a lot of surfaces which is created because of the cavity. So the biomolecule which is used for biorecognition, and it can just attach from these cavities. Finally, here it's a little bit hard to see, but they're all triangles. It's silver triangles. They are stacked with each other because they are on the surface, and they're just trying to stabilize it with each other by forming a stack. That's why you're seeing something like this. But each of them are triangles, such as like this. It's not completely, or maybe like this. You cannot see completely the facet, but you need a little bit more complex microscopy images for here. Okay. And the last microscopy thing I want to mention is that I want to mention this IFM, IFM or AFM. It can be, sometimes I can use a French version, sorry. Because in the atomic force microscopy I want to mention, because we have the equipment here in the university, and we can use this force microscopy to characterize any surface. You can also work with the liquid samples, but it's a little bit more challenging. What happens here, you see here you have it, okay, this is the machine, and if you go look at the part which is marked, here you have a tip, mainly something like this. This is the tip that I mentioned, and this tip is actually made from silicon nitride, and then you have a cantilever which is assisted by this piezo here, okay? What you do is you scan the surface, and if you want to have a 3D image of your surface, what happens, for example, oh sorry, in your surface you see that there are some nanoparticles. What happens that every time when the tip encounters with a nanoparticle or with a, let's say, barrier, there's a force between, there's like a molecular force between the surface and the tip, because silicon nitride is an active material. And by just checking the piezo position, you can measure the force, and you can create indirectly a 3D topography image of your surface. This is an IFM image, and this is a TEM image of the same surface. It's exactly the same thing. In one case, you have a 3D topography, you have an information about height. But in the other one, you don't have any information about the height, because you're taking directly the image from the top. You cannot know what's happening in the depth region. Okay? That's why this tool can be quite interesting to characterize a material when you want to see what's happening in the depth. Okay? Let's come to the nanonetworking part. Okay, this is up to now it's mostly about analytical chemistry, physical chemistry, nano production. And why I explain you all these techniques, that's the important thing, because we're using them mostly in nanonetworking. In nanonetworking, I'm sure Professor Tugcu can explain this better than me. Most of the work that has been done up to now was theoretical, okay? And we know that what's happening in the theory, but we don't know what's happening inside the human body. But the thing is, it's not so easy to enter inside the human body. You cannot characterize anything, what's happening, and the flow or the I don't know, the information can be carried. So what you can do close is you mimic your environment, you mimic your human body, you mimic your veins, and you create a test bed that you can then adapt inside the human body, all right? But first we have to understand what's happening, experimental point of view. So that's why to be able to work with such a system, what you have to do, what we want to do, we expand the limitations again of the single nanomachines by just making them work with each other, and they have to communicate with each other. So, and we want them to enter where we want, just go wherever we want, and then interact with the environment, not passively stay there. So your nanomachine can go, stay where you want, and then disposed by the human body. So it does not work like this. We want them to work really smartly. That's why, as I say, we want, for example, for each of them to share the information. One nanomachine should inform the another one for the task he or she or it achieved, let's say, and then say, okay, enough. We have the enough, for example, for drug loading. We have the enough concentration, enough molecules, stop for the next one. Well, what we can use inside the human body? You can use the electromagnetic communication. It's not so actually beneficial because you're working in the human body, and by implementing something electromagnetic inside the human is not actually the smart way. You can do optical communication. One of them can send, for example, incoming light by Morse code to say to stop. But of course it doesn't work like this, so it's not a possible way. Acoustic waves. There is some maybe research, I don't know about it. Like maybe you have to search for it. But again, it's not possible to work in the acoustic manner. So using sound waves to say the stop or come back, it doesn't work like this. So, what is the most smartest way? Using the molecules as information carriers. Again, we have a chemistry. We build the nanomachine by using biological molecules and the molecules and the nanoparticles. And now we are using the molecules now to information to be carried. So still we have a lot of chemistry behind it. So, for the molecular communication, I know you already know the definition, you already have heard it a lot. Some of you are working with it currently. So what is it? For example, imagine the nanoparticles that I showed you before. Remember the gold halo structure? You don't have something inside. It's like completely like an empty shell. Okay, yeah, empty actually inside, and you have a shell. Let's imagine that I trap a lot of biomolecules inside this nanoparticle. And I want these biological molecules to be released from one machine to another one by just an external stimuli. And I want to see if this information is really going to be transferred the way that I wanted. And this is why I'm using the molecules here. It can be biological molecules, it can be polymeric molecules, it can be different kind of things that you can use. So, What I do is I encode the information, okay, and I can check the concentration of the molecules received. I can change the number of metal or molecules or nanoparticles received. You can check different things in the point of receiver. So you have a transmission to the receiver, and finally you just check if really the information is transferred in a correct way. This kind of molecular communication is not actually something science fiction, because biological mechanisms are really using this. For example, one bacteria community is communicating with each other, with another bacteria community, by just using molecules diffused through the air. So this already exists, and we are just mimicking what's happening inside the human body by using the same mechanism. But when you're doing it, when you're building a test bed, what's more actually hard is that you have to, for example, when you're doing this test bed, you have to design a rapid transmitter. For example, your transmission should not take hours or days, and finally your receiver is not able to detect. Okay, you transmit the information. I send the nanoparticles, for example, or my molecules in days, and finally in the receiver I receive nothing. It's not sensitive enough. So I have to build a correct system which should be rapid enough, and the receiver should be sensitive enough. This is quite important. And as I said, the receiver should be sensitive, so that's why I need the right tools to characterize this received information. As I said, for example, if you use optical microscopy to sense the crystal structure of your nanoparticle, you're not going to be able to. But if you want to sense just the number of molecules, this is the right tool. So you have to choose your tool in according to what information you want to receive, in which manner you want to receive. And of course, what we are currently working is that we build something, a test bed, it works perfectly, but we are not able to adapt this into human body. It does not work like this. So what am I going to do with it? It's like there is an information, and I cannot compare with the human body, and I cannot actually enter in the human body and see if this is really the right tool. So it should be adaptable, right? And when I say we have to mimic the human body, I want to mimic, for example, the veins. I want to see if my molecules are diffused inside this micron-sized tubes correctly or not. First, I have to build an environment, right? And this environment can be built by using microfluidics. It's a small chips. I'm sure most of you have seen, and if not, it's like there's some examples here. And this is the one that I left behind in my in the office upstairs. Meaning that these microfluidic devices here, you see there are some patterns. You can directly create the pattern you want to mimic in the human body into a polymeric chips like this, and you can check the diffusion of your nanoparticles or the biological molecules or your nanomachines inside these micron-sized channels, because diffusion inside a micron, the micrometric scale, is not going to be the same as diffusion, for example, in these large pipes. In one cases, you're going to have a laminar flow. In another one, you can have a turbulent flow, or it's completely different. In a micron-sized diffusion, your capillary diffusion is going to be more important because you have a small surface, and there is going to be a lot of contact with the fluid on the walls of your chip, all right, or the veins. But in a large macro-sized diffusion, of course, the flow is mainly in the center. You don't have a lot of contact with the surface, so the capillary or the surface link is not so important. Okay, that's why in our test bed, basically, we are using microfluidic chips, something like this, as I say. We are able to produce different types of microfluidic chips. We are able to produce it by different methods. Okay, you can use different materials, you can use different production methods, and of course this choice of material and the choice of method is important in the final result, what you want in the finally. You can use a glass as to produce something like this for the microfluidics. you can use silicone, or you can use artificial polymers. And of course, all of them have some restrictions. Some of them are high cost. It's really, and you need a really complex production method. You need a complex equipment for this, so it's not quite easy. And some of them cannot be used for long term, for example, for glass, because when I want to change the structure of my chip, my design, I'm not going to be able to, because it's not reversible. But for polymeric, it's cheap and you can produce different shapes, different structures, or whatever you want. So depending on the application, you just choose your material. In our cases, we are mainly using artificial polymers. What are they? Here, it's a PMMA. It's an artificial polymer. It's a acrylate, methacrylate based material. You can see them in, I don't know, in the stores outside when you see the labels written, the name of the store and everything. I don't know how they call it. And this is really like, you can see them in color. It's like really simple material. It's not so fragile. And it's simple methacrylate. You can see this material everywhere. Okay? Or you can use something like this. Here in the behind we have a glass. Okay, this is a plexiglass. It's like a lamp. Okay, but for us, what we have the pattern is this material. It's more soft, as you can see. It's really, you can break it. It's a like PDMS material, and it's a siloxane actually mainly. It's more viscous. All right. When I say, for example, if you want to work with a nanonetworking system with a semi-permeable membrane, like a channel, for example, because our veins are like this, like it passes some of the biomolecules. The molecules can pass inside, diffuse inside through the channel. You can work with the PDMS material, but this one is harder to produce than this one, and more costly. Because for this, you need a clean room facility, you need a complex equipment, you need something called lithographic production. Production is really hard. But they are more, the channels can be obtained more precise way and smaller. So you just choose the application or the material what you want in the final case. And as I said, for the production method, again, we choose the laser engraving, because this, as I say, lithography is expensive and it's hard process. But of course you can use it. But in our applications for nanonetworking, mainly we are working with the laser engraving. 3D printing is another option, but the thing is, with the 3D printers, you are only limited with some of the materials that's compatible with the machine. You cannot change your material easily, okay? And this material may not be compatible with the solution you wanted. Laser engraving is one of the fastest production methods that we have. It's basically using carbon dioxide laser to create a chip like this. Something like this, okay? And what I can tell you is like, you know that there are some t-shirt printing machines. Like you print, I don't know, like anything you want on your t-shirt by using these machines. The concept is the same thing. So what we are doing, instead of using a t-shirt, that we are using a polymeric material, the pattern that I want to create. Something like this. Here is the detail of the technique. What we do is first, we design a channel, what we want, okay? Here it can be designs like this. For example, in this design, we have 1, 2, 3, 4 transmission points. I can do injection from these 4 points, and I can receive the information here. You can imagine this like this. For example, I want to transmit the information from one location, but I don't know where. And I receive the information here. And now I'm trying to understand where is the initial transmission point. You can use this chip like this. Or you want to, for example, characterize the final concentration of the information you wanted, the final receiving point. What is the concentration which is transmitted from the initial injection point? So you use a straight channel. We just create these patterns by using AutoCAD or some other design programs. You can use a SolidWorks, or you can use a CATIA, or a different kind of drawing programs. It's really not important. You just create your pattern, and then we just place our polymer on the machine. You have a big machine which is actually like a closed, because like a simple laser thing. And by using carbon dioxide as the laser source and by just focusing the laser beam by using adichrotic mirrors, we create the patterns like this. We just open some transmission points. There's some holes on it, as you can see here, and you create the pattern you want. But again, this channel is an open channel. See, like you create the pattern, you can touch here. You have a channel which is open, but I want a closed environment. So what I do, I take another material such as this, the polymer. I just press them with each other by using a hydraulic press, which is a little bit hard machine. It's like it just presses. It's like really like you can see in the industry, like a manual, or you can have it for the electronical versions, different cases. And by using a high pressure, 28 tons, we closed our channels, and now we have an environment that I want to mimic. Okay, this is the first part. Do you have any questions up to now? No? Okay. Now I have the channel, but before I create my test bed, I have to do a characterization of this channel. I have to know what's the size of the channel, what's the depth, what's the profile, what's the roughness. I have to know everything about this channel for me to be able to say, okay, this channel mimics this section of human body that I want to work with. Okay. For this, we use different techniques. We use again optical microscopy, right? And this is the optical microscopy image of two different channels we obtain. And these two channels are actually obtained because they're, as you can see, they're different from each other by just changing the laser power. So if I use 100% power, okay, like a large power, I create really deep channels. Like the depth is quite high here, as you can see in this one. But if I decrease the laser power, okay, then I have to, I just lose the channel depth. But in this case, we have more smooth channel. The surface roughness is actually less, meaning that you don't have any like the rough surface. Like when you touch it, you can also feel it, for example, on a surface, if this is rough or not, or this is smooth. So it's like compensation. If you want rough channels, you have to play with power. You have to go to high power. If I want low roughness but more deep, more shallow channels, I have to go to the laser power, which is a little bit low. I think he stated right. And as I said, depending on the system you want, you can produce a material, you can produce a chip like this, and you can have a 3D image, 3D topography of the channels such as like this. What we have here is just we take the images of the same channel at different heights, at different focus. We just combine them, these different images, and then we produce a 3D topography of the channel such as this one. It's just image processing, it's a simple version. And here you can see the profile of your channel, of this channel actually, okay? Meaning that this profile, we have a machine, it's called a profiler. It just gives you the profile in nanometric scale. It's 2 nanometer precision. It just scans your, like something like this, your channel, and it gives you exactly the 2D profile of what you want. This is another detection method. So we use something like this before we construct our test bed because, as I say, we have to know what kind of channels or what kind of environment I'm working with. Finally, if we come back to the test bed, what we do, as I explained you, we do the microproduction by using carbon dioxide laser. We characterize the surface by different techniques. Here I say AFM, but you can use the profiler, you can use the microscopy. Now I have a completely characterized environment, okay, the test bed. What I want to do, I want to inject my messenger molecules in this environment and see what's going on. So, for example, we have here Y-shaped channel. I have a streamline coming from here. A streamline can be distilled water, okay, simple water system. And it's like flow is continuing. And here in this point, I inject my microbeads or nanobeads. It can be anything you wanted or your nano machines. You inject it, and then you want to see what's happening in the receiver. Let's say this section is my receiver section, okay? And as a receiver, I'm using optical microscopy here. So what you're going to record this one. You see here I'm using microbeads as information carriers, and you have the transmitted information. Let's come back. You have the information, actually the molecular diffusion happening through the channel. It's a flow, it's like a laminar flow, and I just record. I just choose this part as a receiver. You can make this reception point bigger, smaller, depending on what you want to analyze or where you want to analyze. And you can record the number of molecules you actually count here in the below section, right? This is one of the output images you can obtain. And now you can combine, if this is really happening inside the human body, by just implementing this system. Now we are in this process inside the human body, as I said. You can use some video processing. This is a bright field image. Like you can say, no, I don't want to use a bright field image. I want to use a fluorescent imaging, fluorescent intensity, because the beads we are using here are fluorescent molecules, the fluorescent beads. So you have a polystyrene beads and you have a fluorescent molecules around it. I can do some video processing, and each second I can check the position of each microbead. Sorry, okay. This is one of the processing that we use, and then I come back to our initial model and the simulations, and to see if really our experimental results are working with the initially proposed theoretical models. So it's like a background check. We are doing this process currently. We just developed, so we're working to improve this point actually for the, as I say, we want to detect it inside the human body. So we're trying to build a more different system. So if you have any example or if you have any idea, please don't hesitate. Our door is open for everybody. So up to now, do you have any questions? It was a little bit more chemistry, right? Sorry. Do you have any questions for the molecular communication point of view? No. Okay. To sum up, as I said, for the nanomachines, you have a lot of barriers that you have to overcome. So you have to use the biological molecules. This is quite important when you're building your nanomachine. And these nanomachines can be, okay, they are helping us to pass the biological barriers, but they're also helping us for biorecognition. For the receptor or for the receiving point, you have to understand that your molecule has to recognize in the receiving point. For example, this can be for the cancer detection or the drug loading or anything. It can have to know where it's going. And biological molecules are used for this. And the SPR property, the surface plasmon resonance, is quite important for us because this property is helping us for externally, when I stimulate my nano system, I need an answer back. So I need to detect what's happening. So SPR is a good way to detect something, what's happening inside the system. And these particles are really potential candidates for the photothermal therapy agents. Currently, there's a lot of active research on it, and in Ireland, they're producing nano anti-cancer systems, like based on nanoparticles, and for each patient, and they're really using it. And now they're in the way to understand if they're toxic, because clinical research has been done. Now they are doing the toxicity research. Of course, because when you're trying to kill something and if it comes back, the cancer, you have to understand because of the toxicity, you have to know what's going on. So you need a complete research. So it takes a little bit of time. And finally, the microfluidics is also quite an important method of production for the molecular networking, for the nanonetworking. It's because we want to work in a nanometric or the micron scale, and this is the correct tool if you want to mimic what's happening inside the human body. It's quite important for us. And these are some of the references in case you need it. Please let me know if you want to learn more. And I like these images because these are the transmission electron microscopy images, and you can see that when I say we can build anything at Nano, it's real. You can play with the, and lastly, they produce some heart-shaped nanoparticles for the Valentine's Day. It's not a research, okay, for example, like it's not a research focused on the application, but still there is a market for it. So you can even produce heart-shaped nanoparticles.
As a present.
Yes, exactly. It can be interesting for many people, I'm sure about it. So that's it.
I brought millions or billions of hearts to you, kind of.
Yeah, but this is more expensive.
Thanks to Cansu for the lecture. I'm glad that she was able to finish the lecture before delivering her babies because she's in the last couple of weeks.
Last week.
Last week.
Last week, the next week.
We will see for twins, not digital twins, two
That's why it's so big.
young girls.